Hello everybody and welcome to the 5th video in this Blockchain for Beginners tutorial series. Now in this video, I'm going to be talking to you about the limitations of Solidity and of smart contracts and some applications that are very difficult to deploy on the blockchain because of these limitations. Specifically, I'll be talking to you about arrays, strings, for loops, while loops, and why it's very expensive to use those things in a smart contract and how they can actually cause your smart contract to break or to be in a state where it can never be ran again. I'll get into all of that in this video, but before we dive in, I do need to thank Cartesi for sponsoring this video and this series. As I've said many times, they're an awesome company. I've loved working with them through these videos. They've really helped me come up with a great curriculum to teach you guys. So another massive thank you to them. And with that said, let's go ahead and get into the video. Alright, so I'm now on my computer and I am in Remix. In front of me, I have a very simple smart contract. And what I'm going to be doing in the first part of the video here is talking to you about arrays, strings, for loops, while loops, and then finally structs. Now, after we do that, I'll talk about some of the limitations of Solidities and expenses in using these different features. And then we will talk about some potential, fixes or solutions for these limitations. So let's begin by talking about arrays. So the way you create an array in Solidity is you define the type you would like to be inside of the array for all of the elements. So in this case, I'll say uint. You put your square brackets like this. If you wanted a multi-dimensional array, you do another set of square brackets. And then what you can do after this is put the name of the array or the modifier. So I'm going to do something like public ARR, and then I can just close it off like that. So there you go. I've just now created a dynamically sized array in Solidity. So in Solidity, you can have both a statically sized or fixed sized array or a dynamically sized array. If I do something like this, where I just have square brackets with no element inside or no value inside, this is dynamically sized. So this means it will grow as I add more elements to it. Now, if I do something like 5, this is going to say this array can only have 5 elements inside of it. And I will initialize those elements, I believe, all as 0. All right, so that's the basics for arrays. Now, arrays are a reference type in Solidity, and that means that they are mutable and we can modify them once they have been created. So we have direct index access. We can access the length of elements or the length of the array, and again, we can push elements inside. Okay, so let's just deploy the contract right now and have a look at how we actually access the elements in this array. So I'm going to deploy this. When I go here, notice I'm going to have ARR, and then I can pass the index of the element that I want to access. Now, arrays are 0 indexed, so if I do something like ARR and 0, it's going to give me the value 0, because since we statically initialize this array, we're going to have 1 element with value 0, 5 elements with value 0 inside of the array. Now, let's access index 1. Okay, we get 0 again. Let's do index 4, 0 again. Let's do 5. And then notice here that we actually are going to get a revert. The transaction has been reverted to the initial state, and that's because an error would have occurred because we're accessing an index that is out of the bounds of this array. Perfect. So now that we have done that, let's look at how we can actually, modify the elements of this array. So let's create a function. Let's say function. I'm just going to say mod ARR, standing for modify array. We will make this a public function, and we're not going to return anything. We'll just actually modify this. Okay, now inside of here, I'm just going to take in a uint x and a uint idx. And instead of x, let's actually just go with value, just so this is a little bit more clear. Now, essentially what this is going to do is change the element at index to be equal to value. So let's just say ARR at index, let's go idx is equal to val. Notice we're not getting any errors, so this should be good to go. Okay, so let's deploy the contract. Let's go here. We're going to look at index 0, see that that has value 0. Now let's change this. So let's pass to here a value of, say, 10 and an index of 0. Let's transact. Looks like that's all good. Now when we look here, notice we have a value of 10. Very basic. That's how you can modify this array. Now what I want to do is create a dynamically sized array. So let's simply change this by removing the 5. And now when we do mod array, we're just going to take in a value, and I'll show you how we can append this value or push it to the array. Pretty straightforward, but you can use the .push method. So I can say ARR.push. I can push the value, which is uint, and now this should be good. So let's try this. Let's deploy the contract. Let me just delete this one here. Okay, now we have mod array that takes in a value. So let's just pass 1, let's pass 2, and let's pass 3. Now let's look at index 0. Index 0 is 1, index 1 is 2, and index 2 is 3. Perfect, there we go. We just pushed elements into the array. All right, great. So now that we've done that, let me show you how we can get the length of the array. So I'm just going to say function get length. We'll make this an external, and then this can be a view function that returns, and then we'll just put uint like that. And then inside of here, I can simply return arr.length like that. Okay, so this will give us the length. You can just use the .length property. So let's now deploy this contract. Let's go deploy. Let's mod the array by adding 1, 2, and 3. Now let's get the length, and notice we have a length of 3. Now let's add another element. Let's add 4. Get length, we're at 4. There you go. That pretty much covers arrays. I don't think there's actually anything more to go through with arrays. One thing you can do is access individual elements using the index notation. So I can do something like array at 0 is equal to 1. That's perfectly valid. Or I can just do array at 0. That works as well, as you saw previously. Last thing I will mention is that if you want to actually define the literal for the array, so you want to do something like this, use square brackets. So say uint public arr, and then 1, 2, 3. This is different than something like, I guess, C++ or Java, where you would use squiggly brackets. At least I think you use those in those languages. Anyways, in Solidity, you use square brackets to define the elements in the array. Perfect. Hopefully that is clear. That pretty much covers arrays. Okay, so now that we have gone through arrays, I want to cover strings. So let's get rid of all of this. Now, strings in Solidity are very expensive to work with, and same thing with arrays. Arrays are very expensive as well. And in fact, the reason I'm showing them to you last is because mappings are much preferred over arrays. So you pretty much never want to be using arrays or using strings if you can avoid doing so. There is some use cases where you do need them, but essentially you always want to go with something like a mapping as opposed to an array. I won't get into all of the details, but just understand that they cost a lot more gas than something like a mapping. So if you can avoid it, avoid using arrays. And if you want to mess around with kind of the differences in arrays and mappings, deploy a few contracts and look at the actual gas cost in terms of working with arrays versus working with mappings, and same thing with strings. Strings are extremely expensive to use in Solidity, and one of the reasons for that is that a string in Solidity is actually a bytes array. So you can create a bytes array like this. Now bytes are used for kind of a raw data type, and a string in Solidity essentially is a bytes array that's going to be decoded and encoded with UTF-8, just allowing you to actually view the string. So let me show you what I mean. If I do something like string, and I guess we can put public, although we don't really need to, and we'll just make this equal to a hello. We can say this is equal to world. That is completely valid. Now you want to, again, avoid using strings whenever you possibly can because they're very expensive to work with. Same reason with the arrays, because they are actually represented by a bytes array. Now, strings in Solidity are extremely simple. You do not have index access to them. You cannot concatenate them. You can't get the length of them. There's actually almost no methods or properties for strings. You literally can just store a literal string. And in most situations, it's going to be much more efficient, especially if you're working with large strings, to store them off of the blockchain and simply store a hash of that string in the storage of your contract. That will be much, much cheaper than actually storing the string itself in the contract. Anyways, let's deploy the contract here with the string. Notice that I can access this and I can have world, right? I can see world there. So let's create another function. Let's go function set string, and let's go string, and then let's go with value. Now, I'm not quite done with this yet. I need to talk about something with having strings inside of functions. But for now, I will say hello is equal to val. Okay, so notice that I'm getting an error here. Now, why am I getting an error? This function actually looks pretty valid, right? I have my string parameter, I have this public, I'm setting a value. This should be good. The reason why I'm getting an error here, we can hover over this, is because the data location must be memory or call data for a parameter. So this is where I'm going to talk about the different storage locations that you have in your contract. So in your contract, you have state or storage. They're kind of the same things, storage/state. Now that essentially means that you're persistently going to be storing this data in the smart contract itself. Now, any data you store is going to cost you small amounts of Ethereum, right? It's going to be more expensive to store more data than to store less. You want to store the least amount of stuff that you possibly can. So that's the first location, storage/state. That's persistent. It's always going to be there. The other location is memory. Now, memory, similar to your computer's RAM, is a temporary location that's only going to be used when the contract is actually executing. So when I'm using a reference type like a string, I need to specify it's going to be stored in memory. So I'm going to say memory like this. So as soon as I put memory, we actually would have seen this before, I think. Now this is valid because it's saying I want to store this parameter in memory as opposed to in the state or storage of the contract. And you only need to specify this for reference data types. So same thing with arrays. Let's say I did something like uint, and then I wanted to have my value like this. I would need to now specify memory to not get yelled at by the compiler. Okay, so let's go back though to what we had before. String memory value, hello equals val. Let's deploy this. Let's look at this. Let's go hello world, I am Tim. Let's set the string. Let's look at hello, and now we have hello world, I am Tim. Awesome. Again, avoid using strings. If you need to use a large string, what you want to do is store it off the blockchain and simply store a hash of that string on the blockchain. That will be much cheaper. Okay, so now we've gone through arrays, we have gone through strings. I want to show you looping, and then I will show you the gas costs associated with a lot of these different features. I'm just trying to give you kind of the basics right now. Okay, so let us, should we loop through an array? No, let's just loop over kind of a range of numbers to start. So I'm just going to say function, and I will say loop, and I'm going to take in uint n, and all I'm going to do here is simply loop over n numbers. So to do a for loop in Solidity is similar to pretty much every other programming language. You can say for, and then you can define your looping variable. So I'm going to say uint I. I'm going to say I is less than n, and then I'm going to say I plus plus. Okay, so I'm just incrementing I by 1 in every iteration. And then what I'm going to do here is, I guess we can just add to some variable or something because I'm just trying to illustrate looping. So I'll do something like uint sum is equal to 0, and then sum plus equals I, and I think that should be good. And then if we wanted to, we could return the sum, but this is fine. We'll just do this for now. So I just had to take a quick cut there because my cat was freaking out at me for some reason. Anyways, that is now resolved, but continuing here, we're getting a warning. The reason we're getting a warning is because this can be restricted to pure. The reason for that is because we're not actually modifying or accessing the state of the contract. So I just want to put pure like this. Anyways, this is how you do a for loop. Now, I will mention that the for loops, again, are going to be very, very expensive to run if you're not doing them in something like a pure function, right? In a pure function or something that doesn't require a transaction, it's not going to cost you Ethereum to run this. However, it's going to be very expensive to implement for loops when you're actually working with the state of the contract. Now, the reason for that is whenever you do a transaction, you need to pass gas along with that transaction, right? And the gas cost is the sum of all of the operations that the contract is doing. So in this case, it's going to cost me gas to actually add a number to another number, right? For me to add two numbers, that costs gas. But here in this situation, the amount of gas this would cost if it wasn't a pure function is n multiplied by all of the gas used inside of the for loop. Now, that might not seem like a lot, but if n is a large number, say like 1,000 or 10,000, and the amount of gas in here is 4 gas, 20 gas, 100 gas, something along those lines, you can see how the amount of gas required adds up very, very quickly, and it becomes unfeasible to actually be able to loop inside of smart contracts. And in fact, there's actually a maximum amount of gas that you can pass to an Ethereum smart contract. I believe right now it's at 30 million gas. In fact, I think that's right here. It's the gas limit that's showing up. Regardless, you can only pass so much gas. So if your smart contract needs to do a ton of computations, you have to have multiple transactions to be able to complete that because you need to pass the required gas, and you can only do a certain amount of gas in each transaction. Anyways, that was kind of it for for loops. I just wanted to show you the syntax. This is the basics of for loops. Now I will show you while loops. So let's do a very similar thing here. Let's just manually declare I. So uint I is equal to 0. We'll say while I is less than n. We'll say I plus plus. We can do that at the end. And then we'll say sum plus equals I like that. Perfect. There you go. This is a while loop. Again, not really going to explain this. I'm sure most of you understand how this works. Anyways, those are for loops and while loops. And now that we've looked at those, I want to write a very simple smart contract that's going to work with arrays and for loops or while loops and show you how much gas it actually costs on an Ethereum test network. So let's start by just initializing an array here. And let's just say uint, and let's go ARR, and let's just make this equal, I guess actually I can just define it like that, uint ARR. That's fine for now. Then I'm going to have a function. I'm going to say function create ARR. I'm going to say uint n, and I will go with string value. And I'm actually going to change the type of this array to be a string array and show you how expensive this gets. Okay, now I will make this public. Now, what I want to do here is essentially initialize this array with n elements that are equal to this string value. Now, I need to remember to add my memory keyword, otherwise it's going to get mad at me. Okay, so let's do this. So what I'm going to do is write a for loop. I'm going to say for, Again, this will be I, u int I. This is going to be I is less than n. Let's add a space here, and then I plus plus. Okay, now what we'll do is say arr dot push, and we're going to push the value like so. Okay, so right now we can technically run this infinite number of times, and I'll show you what happens if we try to do that, but I want to deploy this to our injected Web3 to the GoReli test network. So it says custom network right now. Let me just go to my MetaMask and change this to GoReli, and then we will deploy this and test it out. All right, so we are back on GoReli. I'm going to deploy. Let's see how much this is going to cost us right now. Okay, so not a significant amount of gas because obviously we haven't done any computation yet in the contract. And then once this is deployed, we'll actually try running this method and see how much gas it costs us. All right, so it looks as though the contract has been deployed. We can see it down here. It says create ARR. Now let's just see, again, this is going to be kind of anecdotal. I'll just go through a few examples here. How much it costs to do one that has 10 elements and the string hello world. Now I need to quote the string here, so let's do that. And let's transact and see approximately how much this costs us. So when I do this, notice we're getting 0.006876, okay? So we can kind of copy that and keep that in mind. And then I'll show you how this is gonna, I guess not exponentially, but go up a lot as I increase the value of n. So let's now do one that has 1,000 elements and see how much this costs. So when I do transact now, we're going to see that now we're at 0.05. Now, if you actually put that into the price of Ethereum, 0.05 Ethereum is a lot. Now, I'm not sure if it would be the exact same on the regular Ethereum network, but the point is you saw how we drastically increased this to a whole decimal point, right? Just by making this 1,000 instead of, say, 10. And then let's go crazy and let's make this something like 100,000 and transact and see how much this would cost. And here it tells me we actually cannot even send this amount of gas. The transaction will likely fail. So let's go to 10,000 and see if 10,000 is doable. Same thing, we can't even do 10,000. Let's try doing something like 5,000 and see if that's gonna work. Okay, 5,000 doesn't work. Let's try 25,000, transact. Okay, that's not gonna work. So just trying to show you here that we really cannot do a lot of looping operations. And even if we try to do a lot of looping operations, that is going to be very, very expensive to the point where it really doesn't make sense to do them inside of the smart contract. All right, so now that we've gone through those few examples, just so you can see kind of in the real world how much the gas is going to cost, let me delete all of this and show you that Remix can actually give us a gas estimate for specific functions. So what I can do is something like, let's go uint x is equal to 0, and let's go function set x. Let's take in a uint value. Let's just make this public. And then what we can do is say x is equal to value. Okay, so this is my function. Very, very simple. All we're doing is assigning a variable. Now, if I hover over the function name, notice that down here, kind of in the right corner, or I guess not really corner, but right on the console bar, it's showing us the execution cost is going to be 22,498 gas. So that's a significant amount of gas considering we're only doing a very simple operation. All right, so now that we've seen that, let's just do a few more examples and estimate some more gas costs. So another thing we might want to do is evaluate a condition. Maybe we want to use a require statement or something like that. So let's just do something like require, and we'll say val is greater than, and let's just go with 10, and then we'll say val is too low. Okay, put our semicolon. Let's see how much gas it's telling us now. So if I hover over here, now you can see the gas has increased a small amount. So the require statement doesn't really use that much gas, right? Now let's see what happens if we try to add a number. So let's do something like x plus equals val multiplied by 10. And let's look at the gas estimate now. And notice it's giving us infinite gas. Now, whenever you're seeing infinite gas, that usually means that Remix is not able to estimate how much this is going to cost. Now, in this case, the reason it's saying infinite is because val can be any single number. Now, if val is any number greater than 10, when I multiply this by 10, Remix has no idea how much this computation is going to cost, because the larger value is, then, the more that this is going to be, the more gas this is going to cost, because the more addition operations we need to do. Essentially, whenever you're doing multiplication, you're really doing repeated addition. And well, the more repeated addition, the more gas this costs. So infinite gas is just telling you it could theoretically be anything. And you really want to try to limit these functions so that they cannot cost infinite gas. Because if they cost infinite gas, you could do a transaction that will never be able to run because you can't pass enough gas to actually be able to execute it. All right, hopefully that makes a bit of sense. I just want to give you a quick example of the gas costs and how quickly they go up using smart contracts. Now I will talk to you about structs, and then we'll talk about some programs that are really limited on the blockchain because of the fact that we can't really do any looping, or at least not very efficiently. All right, so to illustrate structs to you, I first want to start by showing the alternative to structs, which would be actually representing objects using contracts. Now, contracts, just like classes, can be instantiated. So I can have different instances of the contract. Now, typically we just deploy a single contract, but this contract can instantiate another contract and then have a reference to them. So for example, I can do something like this. I can have contract person, I can have uint age, string name, uint balance, I can have a constructor, and then I can treat this just like I would any other class in, say, Java, right? Now, from this tutorial class, what I might do is create a function like this, and I might say function create and then person, and then maybe I take in my uint age and then my string memory name like that. And then the balance we would just imagine would be implemented at another time. Okay, then I'm going to say public. And then inside of here, what I can do is actually create an instance of this person class. So I would say person equals new person. And then I would just pass my constructor values. So this needs to be a string, sorry, age and name. Okay, there we go. I've just created a person instance. Now this is an instance of this contract. Now this looks perfectly fine. However, this is going to cost you a ton of gas because contracts are much more expensive to work with than structs. So instead, what you would want to do is replace this contract with a struct. Now the struct would look something like this. Let's do this, struct, and then we can remove the constructor and just do the following. Now, there's a few other changes I need to make here. So when I'm working with a struct, first of all, I no longer need the new keyword, and I also need to pass a balance, right? So I'm going to pass the balance 0. The reason I need the balance is because this is a required field in the struct. I'm storing an age, a name, and a balance. And if I initialize my struct in this way, then I need to pass all of these fields. I'll show you another way to initialize it in a second. Now we're getting an error. The error is that I need to specify the location for this type. The reason for that is this is a reference data type, meaning it's mutable, so I can change it later on. So I need to specify memory here, just like for my strings. Now, when I do this, notice it's all good. Now it's telling me I can make this a pure function, I believe. Yeah, because I'm not actually working with the state of the contract. This is just an example to illustrate the struct. Now I'm getting a warning here. It's just saying that this can be a pure function because, we're not dealing with the state of the contract. Anyways, this is what you want to do if you want to store like custom data, essentially in a custom type, create a struct rather than creating a contract. So now to really kind of show the use case of a struct, we'll write a very simple contract that's going to allow us to associate an address with a person. So what I'm going to do is put a mapping up here, and I'm going to map an address to a person like that. Totally fine for me to do that, and I will just call this people. So now when I create my person, I will add them into the people map. So what I'll do after I make my person is I will say people at, and then this is going to be the address. So message.sender is equal to person like that. And then of course I would adjust the balance if money was sent into this contract. So now that we've seen this, I'll just show you another way of initializing this person because we don't have to do it in this way. So I can actually remove kind of the literal, written person and just say person, memory person like that. And now I can just specify the attributes on this person. So I can say person.age is equal to age. I can say person.name is equal to name. And then if I don't do anything for the balance, that's completely fine because the balance will be initialized as 0. Anyways, that's another way that you can initialize a struct. Just wanted to show you can do it in this way, or you can actually write out kind of, the main initialization or the constructor initialization where you pass in those values. Anyways, that is pretty much all I had for this first section here. I showed you the gas costs associated with looping and how looping is really a big problem in smart contracts and is unfeasible, especially if you're doing a large amount of computations. I also showed you that storing strings and bytes is very expensive and you don't want to do that. Lastly, I talked about structs here and how if you want to represent kind of a custom object or a custom type, it's much cheaper and better practice to use a struct rather than to use a separate contract, right? Which would kind of act as a class. You don't really want to be doing that in Solidity. There are some use cases, but if we're going to be creating a ton of different people like this, we definitely don't want to be using a separate contract. Now what I would like to do is really focus more on the limitations of Solidity based on some of these things you just saw, and talk about how we would implement something like an order book in Solidity. Now, an order book is essentially what's used when you're trading stocks, you're trading assets of some sort. You want to have buy orders and sell orders and match the buy and the sell orders. Now, in cryptocurrency, you definitely need this. You need a way to exchange your different coins, buy coins, sell coins, whatever it may be. So I'm going to hop over to the Blackboard now, or the drawing tablet, and start talking to you about how we would implement order book in Solidity, a lot of the problems that we're going to run into doing that, and then some of the solutions we may have to actually make this more feasible. All right, so I'm here on my drawing tablet, and I want to begin by explaining to you what an order book is. So an order book is essentially used whenever you're trying to trade something. So in this situation, let's say we're talking about US dollars and then something like Ethereum. Now, an order book just really states the buy and the sell orders for this specific asset. So in this case, with US dollars, we would be buying Ethereum, so these would be our buy orders, and then on the other side, we would have sell orders. Now, whenever we want to actually make a trade, we need to match buy and sell orders together based on the price. So when I put in a buy order, I need to specify the price that I want to purchase Ethereum at. Now, what I would do is something like 1 Ethereum, and then I want to buy this at maybe 4K, right? That's the price that I'm willing to buy this at. I put that buy order into the book. Now, maybe someone wants to sell Ethereum. Maybe they're selling 1 Ethereum, and maybe they want to sell it at like 4.4 thousand. Well, if this is the case, we cannot match these two orders together because they have different prices. Now, you can probably realize just by looking at this, it's going to be very difficult to actually match buy and sell orders, because the probability that two people are going to have the exact same price in mind for this specific asset, well, that's just very rare. The seller is always going to want to sell high, the buyer is always going to want to buy low. So because of this situation, we can use multiple buy orders or multiple sell orders to fill either order, right? So maybe I have a ton of small buy orders, something like 0.1 Ethereum. Well, if all of these small orders allow me to actually fill one large sell order, then I would use, all, let's say 10 of these to fill this 1 Ethereum order. Now, of course, they have to be at the same price, and so we end up running into the same problem again. Now, this is where we talk about something called market makers. So I'm going to draw this right here, market maker. Now, a market maker essentially provides liquidity to this trading pair or to this order book because, as I was saying, it's going to be very rare to have our buyers and sellers agreeing on a price. So the market maker is actually a neutral entity that's always willing to buy and always willing to sell. Now, they have incentives to do this. They will earn some rewards, some fees, whatever it may be. But the idea is they're always buying and they're always selling. And this allows liquidity in this market. They make the market. It allows me at any point in time to go and buy my Ethereum or sell the Ethereum. Now, the market maker is pretty well dictating the price of this asset based on the pressure to buy and the pressure to sell. Now, I don't want to get more into this because it's a bit beyond my scope of knowledge and finance and all of that. But that's the basics of an order book. And now we'll talk about how you would implement something like that on the blockchain. So, of course, an order book is pretty important, especially when we're talking about cryptocurrency. People want to buy and people want to sell. So let's draw out another order book right here. And I'll talk about how we would actually kind of do this algorithmically. Because, of course, although this was done manually in the old days, we now have computers that do this for us, and they can do it very, very quickly and efficiently. So let's say we have a bunch of buy orders over here in green. We have a bunch of sell orders here in red. Well, the first thing that we should realize is that since we're going to implement this as a smart contract, if someone is going to be making, say, a large sell order, maybe of 1 Ethereum or maybe a lot more than 1 Ethereum, they're going to have to use usually multiple buy orders to fill this sell order. So they may have to actually loop maybe 20, 30, 40, maybe 500 times to actually fill their order. And as we saw previously, looping is very, very expensive. And so the more looping we have to do, the more it's going to cost whoever's performing the transaction. Now, we also may run into a problem where someone needs to loop more times than is allowed in the smart contract based on the gas limit. Let's say I want to make a sell order of maybe 100 Ethereum. Well, the chances that someone else is going to be buying 100 Ethereum is slim. Maybe there's a ton of people buying a small amount of Ethereum. So I might have to loop, say, 2,000 times. Now, if the maximum number of loops I can do in one iteration of my smart contract or one call, of my smart contract is 100, then I'm going to have to split this into two separate orders to be able to actually make this sell, right? I'm going to have to do two 50th sells because I can only do 1,000 loops in one smart contract transaction. So that's kind of the main problem we're going to run into here, and it really just has to do with the ability of looping with the smart contract. Now, this is kind of a naive perspective because this assumes that everyone interacting with this contract is interacting with good intentions. They are a good actor. Everyone wants to buy, everyone wants to sell. They're not trying to manipulate the market. But of course, people are always going to try to manipulate the market. And one way they could do that with something like this is they could put in a ton of tiny buy orders. So let's say we have some buyer who's really trying to kind of lag the smart contract and make it take a very long time or be very expensive to interact with. Well, the way they would do this is they would put in a ton of fractional kind of bogus buy orders, and they would do this many, many times. Let's say maybe they have 1,000 of these orders. Realistically, it would be way more than that, but they have a ton of these orders that they're adding. They're all very small buy orders. Well, now, even if I want to make a relatively small sell order of, say, 1 Ethereum, I have to loop thousands of times, in this case, probably hundreds of thousands of times, to actually be able to fill this order because there's so many small buy orders. So now, again, that requires me as the seller to split this into very, very small amounts to be selling. So maybe I have to sell this amount at a time because I just cannot do enough loops in my smart contract transaction. So that's kind of a main problem that can arise here. You can have people try to manipulate the market, and when someone does this, if we're not handling this correctly, it's going to cause the seller practically to not be able to sell because it's going to take them so long, and it's going to cost them a lot of money to do that. So the way that we de-incentivize this type of behavior is we put the burden of looping on the buyer. Now, the seller is still going to have to loop to fill their order, but we try to make it so that less small buy orders come in by kind of penalizing those. So for example, if we want to purchase 1 Ethereum, what we do as the seller is we loop through buy orders, hopefully in an efficient manner, and we mark all of the orders that we require to fill this sell order as executed. Now, when we mark them as executed, that essentially means that we've made the trade. So we immediately take all of the USD funds, we give those to the seller, but then we lock this asset in the smart contract, and we require that the buyer do as many transactions as they originally did to buy to be able to take their stock back. So what I mean by that is if they did 1,000 of these tiny little transactions, they need to do 1,000 more transactions to retrieve all of those funds from the smart contract. So for example, if they want to take whatever it is they bought for, 0.0001 USD or ETH or whatever it's going to be, then they need to do 1 transaction, and that will give them whatever the amount of stock that was traded in this specific trade. Hopefully that's making a bit of sense, but they will take this amount of Ethereum, they'll get that from this 1 transaction, then they have to do this 1,000 more times because they had so many orders. So for every order, they need to do 1 transaction to retrieve all of the funds that were traded in that specific order. So this now puts the burden of looping on the buyer and hopefully de-incentivizes them from doing this. Now, of course, we still have this underlying problem that the seller needs to do looping to be able to actually fill their sell order. So we need to come up with an efficient way to do this, and that's what I want to talk to you about now as we head over to the other screen. So to reiterate here, the main problem that we're running into is that we're requiring a ton of loops to be able to perform buy and sell orders. And even if we implement that previous solution we talked about, the seller still needs to determine which buy orders to match with to be able to make the sale, right? And then we have to mark orders as executed. We have to store these orders somewhere. How do we do all of that? That's really the question right now. And how do we do it in an efficient manner? Because we can't have nested for loops. We can't have any crazy algorithms that are taking really long time to run. That's just not feasible on the blockchain and with smart contracts. Now, solution 1 is really the approach that has to be done on the blockchain, and this is to come up with the most efficient data structures and algorithms possible to implement what we just talked about. We need probably an advanced type of tree that's going to allow us to look for the largest possible orders to fill the largest sell orders, so we only use 4, 5, 6 orders and require a very little amount of looping to be able to make a sale. Now, of course, the same thing happens on the buy side. The idea, though, is that we need to do all of this efficiently. And again, we need to manage our storage efficiently as well because it's expensive to store orders on the blockchain. So solution 1 is essentially be a genius and come up with a great data structure and algorithm that has no bugs, has no problems, is never going to be inefficient, and use that. Now, of course, that's not really the most reasonable approach. Ask me to implement order book. I have no idea where to even start. That's going to be very complicated. I'm going to have to do a ton of research. Hopefully, I'm going to find someone who's done something like this before and kind of copy what they have. But even then, again, this is just really an impractical approach for most people trying to implement something like this. And even if you do come up with an implementation, the first approach is most likely going to be buggy, it's going to be inefficient, and it's probably going to be infeasible to use. So then solution 2 is essentially kind of similar to solution 1. Copy someone else who's already done this. Hope that there's some genius out there who's written a great order book. Just take the exact same order book, maybe modify it a little bit if you were trying to make your own, and use that. Now, again, that's really still not a great approach. You can still have a lot of inefficiencies, and you still might have to loop a ton of times to be able to fill a buy or sell order. Now, the third solution is kind of more of an abstract one, but this would be to use something off the blockchain, maybe like a SQL database that's already very efficient at searching for specific orders. Maybe you write some advanced select query that can kind of give this information to you, and then you store hashes of this on the blockchain, whatever it's going to be. Unfortunately, interacting with SQL from the blockchain isn't really possible right now. At least I don't know how to do that, and so that kind of limits that option as well. So even with the only feasible option, which is essentially have a really good data structure and algorithm, you're still running into problems. Now, you might be asking yourself at this point in time, well, how is this done then? How do people do this if this is such a problem? Now, you can still use an order book. It's just not going to be the most efficient thing in the world. But what a lot of platforms are doing now is using something called a liquidity pool. Now, a liquidity pool has its own issues. I'm not going to talk about those in this video. Essentially, a liquidity pool is just a store of a ton of the assets that you're going to be trading. So you have whatever asset 1 is and asset 2, you have usually an equal amount of them in the pool. And then based on the demand for the specific assets, the price of those assets will fluctuate within the liquidity pool. And the people providing liquidity, so putting their assets into the pool, will be given a type of reward, kind of like a fee that you would pay when you're actually trading them, right? Anyways, that's the liquidity pool. Again, has its own issues, but that's kind of an approach that's being used currently. And really, with that said, I think I'm going to wrap up the video here. Now, I know I didn't talk too much about the solutions, but that's because this video is really focused on the limitations of the blockchain and showing you that a lot of stuff we would like to be able to create that would be way simpler to do off the blockchain, we just can't feasibly do using smart contracts and on the blockchain because of those limitations. Now, even the stuff I showed you at the beginning of the video, strings, arrays, for loops, while loops, those are very inefficient to use. They cost a lot of money. And the reason we left them until the very end was because we don't really want to encourage their use. And I want to make sure that you understand kind of the problems with them and that they do exist. You can use them, but you should be very careful when you're implementing those specific features. All right, so with that said, I am going to end the video here. Another massive thank you to Cartesi for sponsoring this video and this series. In the next video, we'll be looking at specific solutions and how we can actually write scalable smart contracts in decentralized applications. I hope you guys enjoyed. If you did, make sure to leave a like, subscribe to the channel, and I will see you in another one.